Welcome back, my dears. This is the second video for section 2. In this video we'll talk about many topics. First of them is the half-life. The half-life, or T-half, is the time required for the atoms of a radioactive nuclide to decay. Each radioactive nuclide has its own half-life. The more stable nuclides decay slowly and have a longer half-lives. To understand what we have seen here, we will track this nuclide to see the decay in the terms of the half-life for this radioactive nuclide, the potassium-14. The potassium-14 here, this is a newly formed drug. It contains a potassium, argon and calcium. Here we have a lot of potassium which then degraded or decayed to the half of the amount as you see. It's happened at 1.3 billion of years. Wow, it's a very long time. And then half of this amount become halved, and this is the second half-life at 2.6 billion of years, and so on till the third and fourth half-life, which will reach to 5.2 billion of years. So we can say that the potassium is stable in compared with uranium, which have a half-life with a years, not a billion of years like the potassium-14. Here the radium, it's not uranium, it's a radium-226, the amount in milligram, which degraded to the half. Here 20, it becomes 10 after 1599 years, and here it become from 10 it become 5 after 3,189 years, and so on in the third half-life and in the fourth half-life. So here it becomes half, and then half the half, so it become quarter, half the quarter, it become 1/8. And here this table showing some examples of the half-lives of some radioactive isotopes. From this we can say, for example, here the carbon have a half-life of 5.7 times 10 to the power of 3 years, in compared with the iodine, which have almost 8 days. So which is more stable? The carbon-14, which is have the more half-life or the longer half-life. So it's here the carbon are more stable, but when we compare it with, let's say, thorium 230, we found that the thorium have a more value. It's almost 7.54 times 10 to the power of 4 years. So the thorium is more stable than the carbon-14. The half-life questions not just ask about some details like what we have talked about, but it may be in the form of a problems. Let's see this problem and see how to solve it in an easy way. Sample problem B. Phosphorus 32 has a half-life of 14.3 days. How many milligrams of phosphorus 32 remain after 57.2 days if you start with 4 milligrams of the isotope? So let's analyze. We have the original mass of phosphorus, which is 4 milligram, and we have the half-life, which is 14.3 days. The time elapsed is 57.2 days. The unknown is the mass of phosphorus after this elapsed time. So we need to know this time representing how many times from the half-life, so we're gonna divide this number, which is 57.2, over the 14.3 days, so we will have the number of half-lives, and then we will, to know the amount of phosphorus remaining, we will need to multiply the original amount times 1/2 to the power of the number of half-lives. Okay, so the number of half-lives is 52.7 over 14 over 14.3, so we will have a 4 half-lives, and the amount of phosphorus is a 4 milligram, which is the amount times half times half times half times half, or we can conclude all of these halves into 1/2 or half to the power of 4. So the answer will be a 0.25 milligram of phosphorus. Now we will move to the second topic in this section or in this video. It's about the decay series. A decay series is a series of radioactive nuclides produced by successive radioactive decay until a stable nuclide is reached. Simply, let's explain it in a more simple way. You have a radioactive nuclide, which is a very heavy atom, so it cannot be reached to a stable nuclide directly through a direct emission or a direct radioactive decay reaction, but it needs more than one, so it's called a series or a chain of reactions. So the heaviest nuclide of each decay series is called the parent nuclide. The beginning is a parent nuclide, and the nuclides produced by the decay of this parent nuclide are called daughter nuclides. So we start with the parent and then we reach to the daughter nuclides. Okay, here this diagram is the same as what you have in your hardcover at page 650. Okay, for more clear picture, you can see it there for a better picture, then it's somehow not very clear here in the presentation. Here the uranium moves to thorium and the thorium moves to palladium. palladium, okay, and this into another isotope of uranium. Okay, during this moving from uranium and the another isotope of uranium, this is called a series, yes, a radioactive series. So when we need to sort this series from here, the uranium 234, to reach the, for example, polonium, here we have a series from passing through thorium, radium, and I can see it very well, till reaching to the polonium. So this is another series. Okay, so in this series we have the uranium as a parent, and each one of these is called a daughter till reaching the target one, which is the polonium. The final topic is called the artificial transmutations. Artificial radioactive nuclides are radioactive nuclides not found naturally on Earth. They are made by artificial transmutation, which is a bombardment of nuclei with the charged and uncharged particles. Naturally, there is some radioactive nuclides, and we need for applications, we will talk about this in the next two sections. These applications need another radioactive nuclides which is not present naturally, so we need to manufacture, or we need to make them artificially. So we need to hit these nuclei or strike them with charged and uncharged particles with a high energy and a very high speed, which allow these particles to enter to the nuclei to form the new artificial radioactive nuclides. Some of them are transuranium elements, which is element with more than 92 protons in their nuclei. Artificial transmutation are used to produce transuranium elements. So now we have finished section 2, and let's move now to the questions in our worksheet. Okay, let's move to number 5. What percentage of the original amount of carbon-14 remains in a 20-gram sample after 2 half-lives? Here we ask about the percentage, and we have two half-lives. So when we are talking about 2 half-lives, so it becomes from 100 to 15, and then in the second half-life it turned from to 50, so it's come from 50 to 25%. So the answer is 25%. Okay, now in the second page, question 6 and 10 till 10 refer to the following table. Half-lives of several radioactive nuclides are shown here. Manganese 56, palladium 148, silver 102, zinc 62. Their half-lives respectively are 3 hours, 5 days, 70 minutes, and 9 hours. So, for number 6, Which nuclide decay the fastest? When we say decay the fastest, that means it's have a shorter or longer half-life. Has a shorter half-life. So which of these elements have the shorter half-life? As you see, it is a silver. It have only 70 minutes half-life. So the answer is C, silver. Okay, now which of the nuclides is probably the most stable? Manganese, palladium, silver, zinc. Okay, let me give you a hint. When we say it's the most stable, we say it have the longest half-life. So it would be the one containing days. It's a 5 days compared to 9 hours and 3 hours and just 70 minutes. So it will be the palladium 148. So when we move to the next question, which is number 8, if there is an equal mass of each nuclide at the start, which nuclide will have the least mass after 5 hours? This question is typically like the question number 6. In question number 6, he asked about its decays the fastest, and here he said you will have the least mass. The least mass means that like it decays. So the answer is like the answer of number 6, which is the silver 102. Okay, number 9. What fraction of the original mass of palladium 148 will remain after 10 days? So let's get back to the table to check about the half-life. The half-life is 5 days. So when we are talking about 10 days, these 10 days representing okay, let me explain it. We starting with an amount, let's see, it's 10 milligram. Then we have a 5 days here, and then it will reach to 5 milligram. Then after the second 5 days, it will reach 2.5. Okay, so this is the first half-life, and this is the second one. So we can say it's reached the fraction of 2.5. We have a 10 over 2.5, so it will be yes, 1/4. We will reach to the half, and then the half reach to the quarter. Yes, so it will be a 1/4. 10 this is a somehow tricky question. If there is an equal mass at the start, how will the mass of zinc 62 compare with the mass of manganese 56 after 9 hours? To see this question, we need to get back to our board, like here. So okay, so now we will talk about the zinc, which have a half-life of of 9 hours, and manganese, which have the half-life of 3. Okay, so zinc 9 hours, and we will talk about the manganese, which have a half-life of 3 hours. So when we are talking about this element after the 9 hours, it will have only one half-life, and this each 3 hour have another half-life, so it will have one, and then 2, and then 3. So the percentage will be zinc, which have the more half-life, to the next one, which will be yes, so the answer will be C. It will be a 4 to 1. We will start with a first half-life, and after this we will have the second half-life. If we suggest that we will start with the 10 milligrams, then it will be 5, then it will be 2.5, then it will be 1.25, and this for the zinc it is 10, which then go to 5. So when we comparing this one, okay, this amount, which is 1.25 over the 5, we will reach this, it would be a 4 to 1. So the answer is C, 4 to 1. Thank you for watching, and see you in the next session. Bye bye.